Welcome, everyone. For today's prep, we're going to start looking at the idea of improper integrals. And what we're going to do is we're going to kind of generalize our idea of definite integrals to kind of extend it to where we're calculating the integral over, well, no longer a finite interval, but an infinite interval that extends off to infinity. And we'll also generalize this so that rather than just integrating a continuous function, we handle functions that have an infinite discontinuity. All right, so let's first start with our fundamental theorem of calculus. This was the big one. This is the main theorem that allows us to, well, calculate these integrals that we've been working with. And there's really two conditions here that we've dealt with, but we haven't really fully considered yet. Now that's what we're going to get to. So let's read through what our statement of the theorem. So it says, if our function f is continuous on the closed interval from a to b, well then the way we can calculate this definite integral of the function going from a to b is we can find an antiderivative of our function f. So that's what capital F is here. It's an antiderivative. And then we take our top limit, plug it in, take our bottom limit, plug it in, and then we subtract. And there's really two conditions here. The function we're integrating has to be continuous on our interval. And then we're also dealing with a closed interval, a finite interval here. So there's really two conditions that for this theorem. Our interval is finite. So we have a finite and closed interval. Finite just means it doesn't extend off to infinity in either direction, and closed just means it includes the endpoints. So in order for this theorem to work, as is, our interval has to include the endpoints, and both of these endpoints just have to be numbers. They can't be infinity. The other condition is that our function f is continuous. And so we're going to consider both of these situations if our interval is not finite and if our function is not continuous. And we're going to see how we can extend our definite or our way to calculate definite integrals in both of these cases. So in this prep video, we're just going to start with the interval case here. And we're going to start with one particular direction. So our direction here is when we have this interval starting at a, some number a, and extending to infinity. So this is the case when we have, it's no longer a finite interval, it's an infinite interval. So we have the infinite interval starting at a and extending all the way to the right towards infinity. For right now, we're still going to keep this continuity condition. So our function f is still going to be continuous on this interval where x is greater than or equal to a. So this is just another way to write our infinite interval here. And the way we calculate this integral, this is our improper integral now. The way we're going to calculate it is, well, it's kind of a two-step process. So we're first going to just calculate a regular definite integral starting at a and extending to some number b. And then, as usual, when we deal with infinity, infinity is not a number. We have to kind of sneak up on infinity. And the way we sneak up on it is with a limit. So what we're going to do is we're calculating this regular definite integral from a to b. And then we're going to move that endpoint. We're going to move the goal line further and further away, further and further to the right. And just a little bit of wording here. We know that whenever we're dealing with a limit can either exist or it does not exist. So if we can calculate this limit, we get a finite number, then we say the improper integral is convergent. And if the limit does not exist, then we say the improper integral is divergent. So again, what we're defining here is this improper integral. So it's really, the definition here is it's really the limit of a regular definite integral. All right. And kind of a way to interpret this, it helps to have a picture. So our area interpretation here, and this is for a non-negative function. So we're going to assume, just for this little picture, that our function here is non-negative. So it sits above the x-axis for all x greater than or equal to a. And so the way to think of what this improper integral does is the improper integral gives us the area it's going to give us the area under f for x greater than or equal to a. So we, on our little picture here, if we're starting at some number a, and what we're doing is the improper integral essentially calculates for us the area of this region that extends infinitely far to the right. So, this is kind of an unusual thing. How can a region that extends infinitely far in one direction, how can that have a finite area? Well, it's kind of surprising. We're going to see sometimes it does, sometimes it doesn't. But the idea behind our definition, again, it kind of helps to have this picture. The idea here is, rather than trying to do this whole thing all at once, try to get this whole area extending infinitely far to the right, the idea here is we're going to calculate the integral, just a regular definite integral, starting at a and ending at b. And what that does for us is it's going to calculate the area for this bounded region. Doesn't extend infinitely far in either direction, so we're going to find the area for this region here. But by doing the limit, we're going to move this goal line here. We're going to move this right side of our region. We're going to move it further and further to the right. And we're going to see where are we going? Where does the area calculation go? Some cases, this region will have a finite area, which is surprising because it is an unbounded region, extends infinitely far to the right. But sometimes we'll see our region just kind of gets really big, and the area goes to infinity. All right, so let's start with our first example. We're going to calculate this improper integral. So it's the improper integral. We're going from 0 to infinity. So we have this finite or infinite interval, and the function we're integrating is e to the negative 2x. So let's see the process. So let's start by change my pen there. And let's start by writing our improper integral. And our very first step is we have to use our limit definition here. So we're going to rewrite this as a limit. So we're going to do the integral from 0 to b. So we're going to keep our bottom endpoint here, the a value. We're just going to keep that fixed at 0, but we're going to extend the upper limit here. So we're going to ultimately watch what happens as b goes to infinity. So we're just using that our limit definition for this improper integral. All right, so that's step 1. So we want to rewrite our improper integral as a limit. So now we just kind of tuck this limit aside. So we're going to keep writing it in every step, but we forget about it for a little bit. And what we really do is we're just going to concentrate on doing this regular definite integral. So that's our next step. Our next step is to calculate that definite integral just like usual. All right, so let's see. So we're still going to write the limit sign. We got to write it every step, but we're not going to deal with the limit until we're finished calculating this thing. All right, so well, what's our usual process? Well, we got to get an antiderivative. So the antiderivative of e to the negative 2x, this is a k-form function. So it ends up being e to the negative 2x, and then we take that constant k that's in front of the x, and we flip it and put it in front of our e, so negative 1/2. So this is our antiderivative, and we're going to evaluate this antiderivative from x equals 0 to x equals b. Okay, so let's do the evaluation. Again, we're still writing that limit sign. So when we evaluate, top number gets plugged in first. So we end up with negative 1/2 e to the negative 2b. Then we subtract, and we plug in the lower limit. So we plug in 0. So we get negative 1/2 e to the 0. And maybe clean it up a little bit. So first of all, we have a double negative here, so I like to just simplify that to a positive. And then e to the 0, we can simplify, that's just 1. So if we rewrite this, we end up with the limit as b goes to infinity. And when we have a positive number and then a negative number, I like to put the positive number first, just so I don't lose track of any negatives. So I'm going to throw the 1/2 in front. And then we have the minus 1/2 e to the negative 2b. So all we've done is just our regular definite integral steps. Get the antiderivative, evaluate the antiderivative just like you normally would, maybe simplify the evaluation, move things around if you need to, simplify. And then our last step is, once we get this in a nice form, our last step is to actually calculate this limit. So that's our next step. Calculate the limit. All right. And to help with this, perfectly fine, we can figure it out from here. But when I have a negative exponent, I like to write that back as a fraction. Just helps me visualize the limit a little bit easier. So I'm just going to do a little bit of rewrite first. So rather than e to the negative 2b, I'm going to write this as 1 over e to the 2b. And I still have that 1/2. Just helps me picture what's going on. So now when I look at this first fraction here is a constant, so it doesn't matter. As b changes, this first constant is just going to stay what it is, 1/2. And the only thing that's going to change in this limit is this second fraction here. So we're thinking about what happens to that second fraction as b gets larger and larger. Well, if b is going to infinity, the exponential function is going to get really big, which is ultimately going to make this fraction really small. So this term here, this is what we would call a c over infinity form. So we have a constant, something approaching a constant on top, and the denominator is getting really big. So whenever we end up with something like this, this ultimately goes to 0. So this is our last step. Calculate the limit. So that 1/2 just stays constant, just stays a 1/2. The second fraction here goes to 0, and we end up with a number. So what this is telling us, the fact that we get a number here tells us that our improper integral is convergent. And if we want a picture, so we have a convergent improper integral. And so we can say then that the value of this integral is 1/2. Now, what does that mean? What is our interpretation of this 1/2? So let's go down to the graph of our function. So here it is. This is the graph of e to the negative 2x. It gets really close to the x-axis, but it never touches. So if you could zoom in, I can only zoom in so far here, but if you could zoom in, you're always going to see just a small gap in between our curve and the x-axis there. But what we've just done is we've just shown that the area for this region over this interval from 0 to infinity is, well, it's the value of the improper integral. And we just showed that that improper integral had a value of 1/2. So this area for this region starting at 0 and extending infinitely far to the right, again, even though it kind of gets hard to tell here, there is a small little gap in between our function and the x-axis. So our region here does extend infinitely far to the right. That region still has a finite area. So we have an unbounded region with a finite area. Kind of surprising. Very surprising. So in interpretation, if I could just like slice this region up and move it all around, technically I should be able to fit it all into a box with area 1/2. So when I slice it up, you know, I'm going to end up with a whole bunch of very small pieces, and I'll be able to fit them all into a box of area 1/2. Kind of surprising that this region that extends infinitely far in one direction, keeps going and going and going, has a finite area. Well, what we're going to see in class is this is not always the case. So in the next example, we're going to do this improper integral, 1 over square root 3x plus 5. We're going to do this one in class. Again, it's going to be an infinite region, so starting at 2 and going off to infinity. And what we're going to see is, well, this region is unbounded, so it's going to extend infinitely far to the right. But, and I'm going to spoil it, this region is going to have an infinite area. The function's decaying, but apparently it's not going to be decaying fast enough for this unbounded region to have a finite area. But we'll go through the calculation in class. So we'll see you then. Bye-bye.